Alright guys, thank you very much for tuning into this video. The idea here is just to finish up the last couple slides from Friday afternoon that I wasn't able to get to. That should help a bit with the homework and also understanding just kind of the basic concepts and theory behind this last section of the chapter. What I am going to do is briefly review what we talked about Friday before I dive into the new stuff though. Alright, so where we left off on Friday was we were looking at the Taylor series expansion for arctangent of x. Of course, the Taylor series for arctangent of x is an infinite series. Unfortunately, that's not very practical to work with in real life, and so what we did is we truncated that infinite series, and we were working with a degree 5 Taylor polynomial for the arctangent of x. And what we realized was, hey, we want to know if this degree 5 Taylor polynomial for arctangent of x is, really accurate, or if it's way off, and we need to know, how close or how far off it is. What we had been doing for the first few days of the chapter is we were doing percent error actual minus estimate over actual to figure out if our Taylor polynomial was good or if it was just way off the mark. The problem with doing that, which we talked about on Friday, was if you're computing the actual value to figure out if your estimate was a good estimate or not, then you might as well have just used the actual value to start with. So there's some weird circular logic. So what we need is an error estimate for our arctangent approximation using the degree 5 Taylor polynomial. We need some way to estimate the error in the same way we need some way to estimate the function itself. And what we came up with was that if we look at the tail of this series, the remaining terms that we kind of cut off, if it was an alternating series, then the next term that we missed, the next term after our truncation, was a good bound for the amount of error we had. Basically, we have no more error than is contained in the next term after our truncation, in this case the degree 7 term. And the way that we explained this is look at how the series here for arctangent of x, the series expansion for arctangent of x, evaluated at point 8, is an alternating series. So the idea is, at each term, like the biggest term in the list right here, this is the entire series, but the biggest term that we see right here is at point 8. Then the next biggest term is 0.8 to the third over 3. Then the next biggest term is 0.8 to the fifth over 5. And this is an alternating series, right? It's plus minus, plus minus, plus minus. So wherever we truncate, the tail of that series is going to be no bigger than, in this case, the degree 7 term, because after that we have the degree 7 term plus the degree 9 term, then minus the degree 11 term. It's just going to be kind of bouncing around in there. I could show that with some decimals. So if you take a look right here, what I've done is I've actually just computed the decimal values for the degree 1 term, the degree 3 term, the degree 5 term, so on and so forth. And you can see how they kind of telescope, how they kind of fit in with each other. We have 0.8 minus 0.17 plus 0.06 minus 0.029 plus 0.0149. And so what's happening is that the terms are going plus minus, they're alternating. And then they're kind of nesting together because not only are they alternating, but they're getting smaller each time. So basically what I'm claiming, all I'm saying is this 0.0299593, I'm saying that term itself is bigger than if we squish together the entire tail that we have right here. And you can kind of see it happen in this picture on the lower left. So we have, a lot of error, and then if we go to the next term, we have less error. And I'm just going to keep pressing the forward button, and you're going to watch that bouncing around. So the idea is the amount of error we have from truncating. It's sometimes called the truncation error. The truncation error is no more than what is contained in the next term. So you just take the next term from your series, plug in the value you're trying to evaluate at, you put some absolute value bars because error is, we're looking at a magnitude here, right? Like we're looking at the size of the error. We want a positive value no matter what. And we get this 0.02995931. Now, I'm not saying that's the actual error. What I'm saying is we have no more than 0.02995931 difference between our estimate and the actual value. We're saying that the approximation given by the degree 5 Taylor polynomial evaluated at 0.8 is no more than 0.0299 units off. It's actually closer than that. It's actually better than a 4.646% error. But remember, we're estimating the error, and in the process of estimating, we lose a little bit of precision, right? But that loss of precision is also, kind of brings all of this material together, because if we're computing the actual value to test the usefulness of our estimate, then why did we even do all of this? Okay, let's keep moving then. So right here, this was the theorem that you guys wrote down, near the end of class. This is the alternating series remainder estimate. Make sure that you do have this in your notes. You could pause the video if there's anything you need to add from Friday. But this is just a fancy way of saying that the truncation error is less than the size of the next term after the truncation. So if we truncate at degree n, then the error is no more than if we take the degree n plus 1 term and plug in the x value that we are estimating at. And this is awesome for alternating series. As long as you have a series that's alternating at your particular x value, we're in really good shape. The place where we start to run into trouble, and this is where we kind of ran out of time, is what do we do if we have a non-alternating series, and that's what we'll deal with right now. So this will look somewhat similar to your homework. They'll say something like, hey, we've got this function f of x equals e to the 2x, and hey, a reasonable approximation for e to the 2x is this degree 2 Taylor polynomial. 1 plus 2x plus 2x squared, at least when we're using small x values near the center of that series, so near x equals 0. What we want to do, though, is we want to figure out a bound for the maximum error we can encounter when we're working with this degree 2 Taylor polynomial on the interval from negative 0.1 to 0.1, when the absolute value of x is less than 0.1. Remember, this absolute value statement is the same thing as saying we're only looking at x values between negative 0.1 and positive 0.1. Alright, so there's P2 of x, a degree 2 Taylor polynomial. The truncation error comes from the fact that that degree 2 Taylor polynomial is leaving off R2 of x. It's leaving off the tail of this series. We're ignoring an infinite number of terms by truncating. R2 of x is the degree 3 term plus the degree 4 term plus the degree 5 term, so on and so forth. And the issue we're going to run into is that series is not alternating for certain values of x. Like when we plug positive 0.1 into that, we're no longer alternating. So we can't make that same argument about how the error is kind of nesting into itself. But remember, we're trying to estimate the magnitude of R2 of x. We're trying to estimate how big is this truncation error at our particular x values. Since we don't alternate, we kind of lose the ability to use the alternating series remainder estimate theorem. Because what happens is when we're plugging in x equals, say, 0.1 or 0.05, some positive x value, yeah, we've got this degree 3 term, but plus we're accumulating an infinite amount of additional small stuff. And now we know that the Taylor series is converging, so we know that additional small stuff is finite, but it is adding to this degree 3 term. The degree 3 term is no longer an error bound for the amount of truncation error we have. We have the degree 3 term plus some positive extra stuff that's adding a little bit more error on top of the degree 3 term. The lucky coincidence here is we don't really have to worry about this additional small stuff too much. It is pretty small. It's not too difficult to overcome it. And the theorem that we have, it's called Taylor's theorem. It's called Taylor's theorem. Sometimes you'll hear it called the Lagrange error bound. So if you hear Lagrange error bound or Taylor's theorem, they're going to refer to what we're about to use. All right, so what I'm claiming is that our truncation error is the n plus first term plus some additional small stuff that we need to overcome, and the theorem that takes care of it says this. Taylor's theorem, or the Lagrange error bound, says we can overcome this extra small stuff, like all this little extra tail of the series that we are ignoring but has, is positive and is adding more error. We can overcome it by just taking the n plus first term, and we only have to replace one thing. We need to take this a value in the n plus first term and replace it with a number c, where c is some value between the center a and the x value we're trying to estimate. So what this is saying is when we have a non-alternating series and we truncate that series at some point to get an estimate, the amount of error in that estimate is no more than the n plus first term evaluated at our particular x value, and then the only thing we have to change out is this is no longer a. Look at this c value here in this n plus first derivative. Instead of having an a value here, instead of having the center of the series, we need to maximize the value of this derivative at some value c, where c is some value between our center a and the x value that we're trying to estimate. It seems kind of strange, but when you see it worked out in practice, it's not as bad as you might think. So let's try out this one. What we have going on here is the problem we were just working with. So we have this degree 2 Taylor polynomial. We're trying to estimate how much error we're getting, or a maximum amount of error, on the interval where x is between negative 0.1 and positive 0.1. So I'm saying, hey, for any x value between negative 0.1 and positive 0.1, what's the most error I could encounter, an upper bound for the amount of error that I have using this degree 2 Taylor polynomial on this interval. And Taylor's theorem says what you're going to do is you're going to take the next term, kind of like the alternating series remainder estimate. We're going to find that next term in the Taylor series, right? We're going to find the next term after the truncation, which in this case would be the degree 3 term. And we're going to plug in everything as normal, except this third derivative. We need to make this third derivative as big as possible for any value between negative 0.1 and positive 0.1, anywhere between the center and the x values that we're working with. And here it is worked out. I'm going to go to the next slide. You guys took a picture of this already. So you saw this on Friday, but now I'm actually explaining it, right? So it's going to make more sense what you're actually doing. Okay, so here are all of the pieces. What you need to first work out is the third derivative of f of x, which, remember f of x itself was e to the 2x. And so if you take the derivative 3 times, the only thing that's going to happen is the number 2 is going to be multiplied down 3 times. So 2 to the third e to the 2x. Okay, so now we've got this expression. 2 to the third e to the 2c x cubed over 3 factorial. And now we're trying to come up with an upper bound for the amount of error, the amount of truncation error. An upper bound means we want to make this expression as big as possible on the interval we're allowed to work on. And so I need to pick an x value between negative 0.1 and 0.1 that is as big as possible when I cube it. And I also need to make e to the 2c as big as possible for any x value between the center and the x values we're working with. Well, the center is x equals 0. If I plug 0 in for c, e to the 0 is only 1. I can make it bigger than that. And the way I'm going to make this c value, or the way I'm going to make e to the 2c as big as possible for any c value between negative 0.1 and 0.1 is I'm going to plug 0.1 in there. And that's what you can see happening right there. So I've got 2 cubed e to the 2 times 0.1 times 0.1 to the third over 3 factorial. Run that through your calculator, and that's an upper bound for the amount of truncation error we have on our interval when we're using the degree 2 Taylor polynomial to approximate e to the 2x. So that works out to about 0.0016. This is not the actual error. This is an upper bound, an estimate for how much error we could have. And then, one thing to keep in mind is, in general, when you're doing these problems, you're trying to pick a c value that is as big as possible, or pick a c value that makes the derivative as big as possible on the interval you're working on. And since e to the 2x is an increasing function, the reason that I knew it was 0.1 and not any other value was just because I know how e to the 2x behaves. E to the 2x is exponential growth. It's monotonically increasing. That function is getting larger and larger and larger for bigger x values. So I wanted the biggest x value possible. Now there's other functions out there that are not monotonically increasing, and so it's not always the endpoints of the interval. But oftentimes it will be. And so anyway, we kind of finished up this problem. Our truncation error is bounded by the number 0.0016. Now you could go ahead and work out the actual error and see that the actual error will be smaller than what we just estimated, but we're coming up with an upper bound that's acceptable to us. All right, let's keep moving. What you're going to see in this slide is I'm comparing this degree 2 Taylor polynomial, the parabola, to e to the 2x. And you can see that at the center they intersect. And then they start to kind of veer off from each other. And so I'm working in this interval between negative 0.1 and positive 0.1. And I just basically wanted to see what's the furthest apart the red curve and the blue curve can be on the interval where x is between negative 0.1 and positive 0.1. That's what we just estimated. We just estimated the maximum amount. We came up with an upper bound for the maximum amount the red curve and the blue curve can veer off from each other in this small interval where x is between negative 0.1 and positive 0.1. So we had our maximum possible error, but then I'll show you the actual as well. So you can see right there, the actual error that we get. This is the thing that you wouldn't want to work out in practice because it kind of defeats the purpose of all these estimations. But just to illustrate the point, the actual error is less than this upper bound we came up with our easy little estimate, just basically by plugging into the next term and tweaking just that derivative coefficient a little bit. And you can see, the furthest apart the two curves are, the blue curve and the red curve, the furthest they are between negative 0.1 and positive 0.1 is right here at 0.1. And that's just because of the nature of e to the 2x and its derivatives. We could try another problem, just to give you the idea of how to get these done, because they do pop up on the homework, right? We have a very similar problem here. F of x is equal to the natural log of 1 plus x over 2, and we're saying that natural log of 1 plus x over 2 can be reasonably approximated by the degree 2 Taylor polynomial x over 2 minus x squared over 8, as long as we're talking about small x values. And what we mean by small x values are x values that are near the center of that series, near x equals 0 or a equals 0. So in this case, again, we're sticking with an interval where x can be anything between negative 0.1 and positive 0.1, and we're going to bound the error on that interval, and then we'll get a graph of it as well. So there's P2 of x. We're trying to estimate the size of the truncation error, R2 of x. And the only thing that is kind of dicey here, the only thing that we have to be careful with is this third derivative that's going to be part of the next term. We're going to be plugging a c value in here, and c can be any number between negative 0.1 and positive 0.1. And we want to make this third derivative as big as possible, some c value that makes that thing as big as we possibly can on our interval. Let's see, so we can find our maximum possible error using the next term. That's what Taylor's theorem says. That's what the Lagrange error bound says, same thing. So we're taking this next term. It's a little bit more difficult than the alternating series remainder estimation theorem. And the reason it's a little bit more difficult is you're not just plugging into the next term, but you're making this value here in this derivative. You're trying to maximize that derivative, make that derivative as big as possible. So what we're going to find is usually our maximum error is going to be at the endpoints of our interval. Now that's not always true, but for a function like e to the x or natural log, that's an increasing function, or even with a decreasing function, this similar sort of thing. The endpoints are going to be what you're looking for. Now, something like cosine is going to behave differently. You know that near the origin, cosine is as big as it possibly can in the middle of the interval at x equals 0, and it's actually smaller at x equals 0.1 and x equals negative 0.1. So if this was a different function, a different f of x, we'd expect different behavior. But in this case, with a function like natural log, we know that the magnitude of this error is going to be as big as possible at the endpoints of the interval. And in practice, you guys are going to find the same thing when you're doing these problems. The endpoints of the interval are typically where you want to look, unless it's something weird like cosine. But okay, so I actually have to test both negative 0.1 and positive 0.1. Basically, what I'm communicating here is I don't know where the functions are going to veer off the most. I'm going to try to draw a picture for you, but you have your estimate and you have your actual function. And with natural log, I know it's either going to be here on the left or here on the right where the functions are going to veer off the most from each other. But because of these absolute value bars, I don't know the magnitude of the difference between the curves where it's going to be the largest. It's either going to be at either negative 0.1 or at positive 0.1. So I'm going to test them. And you guys will do the same thing. I'm testing at negative 0.1. And I could see that's 4.86 times 10 to the negative fifth. Now let's try at x equals positive 0.1. And at x equals positive 0.1, this is a slightly smaller number, 3.599 times 10 to the negative fifth. Now I'm trying to come up with an upper bound for the amount of error on my interval. I'm looking for the biggest number that I could come up with. So the larger number is 4.86 times 10 to the negative fifth. That might seem kind of counterintuitive. You might be like, well, we want less error. But it's not about the amount of error we want. It's about coming up with an upper bound for the amount of error that we might have on our interval. And so this upper bound is larger than this number. And since we're trying to come up with an upper bound, we stick with that larger number. So the estimated maximum error on our interval is this 4.86 times 10 to the negative fifth. We could express this graphically too. So what you see on the right-hand side of this slide is, in blue, it's the actual function natural log of 1 plus x over 2, and then p2 of x is in red, x over 2 minus x squared over 8, the degree 2 Taylor polynomial. And we're looking at this like small little interval between negative 0.1 and positive 0.1. I know it's actually further in towards the origin than that. But just, for the purposes of illustration. And let me pick a good color here. That'll show up pretty well. So what we're saying is on the left-hand side, right here at negative 0.1, that's when we veer away the most, or we have a larger upper bound for the amount of difference between the red curve and the blue curve. Now you can see the actual error, by the way. Remember that it's kind of silly to compute this because it defeats the purpose of coming up with an estimate. But this actual error is actually 4.329 times 10 to the negative fifth. Our estimate was 4.86 times 10 to the negative fifth. What that kind of illustrates is, yeah, it was an estimate. Yeah, we were coming up with an upper bound. We predicted a little bit more possible error than we actually had. But think about how quick it was to do this computation. This upper bound was really fast to find. And then coming up with the actual error would have been kind of pointless because then we'd have the actual value. I have another picture I can show you, and you'll see this again pop up on some of your homework. What this function is, it's kind of an error function. It's the natural log function minus the degree 2 Taylor polynomial. And by subtracting them, you could see at the origin, or at x equals 0, we're at the origin, because the difference between the actual and our estimate is 0 when we're at the center. And then the error grows the further we get away from the center. And so one thing you could possibly do is, if I was able to, zoom in on this in the same way that you would, like in Desmos or something, we could look at this 0.1 right here. Let me kind of clear out some of this garbage, but Yeah, so if this was Desmos or a graphing calculator rather than a PowerPoint slide, I could theoretically then zoom right in at this x equals positive 0.1, and again at this x equals negative 0.1, and I could look at how far this blue curve is from the origin. And the distance from the origin, the distance from the x-axis, not the origin, the distance from the x-axis at x equals 0.1 and at x equals negative 0.1, that's our actual error. That's an error, the amount of error you have at that particular x value. This is no longer the estimate, this is actual error, right? And, so we could see that the actual error that we'd have at negative 0.1 is going to be smaller than the bound that we had. And so it was a good bound. It was a good upper bound that we came up with. Yeah, so anyway, long story short, the idea here is to come up with the next term in your Taylor series. Even for like a sine function that, it goes degree 3, then degree 5, then degree 7, you still go to the n plus first term. So, if you have a degree 3 Taylor polynomial, you're going to find the equation for the degree 4 Taylor polynomial, or the degree 4 term in the Taylor polynomial. Even though for sine you think of that as not being there, when you plug into that derivative, it's not going to be 0 anymore because you're going to try to maximize it on that interval. So anyway, come up with the n plus first term, plug in a c value into that n plus first derivative to make your term as big as possible on your interval, and you've got your bound. Okay, it just takes some practice, so the more you work with these, the better it's going to go. And good luck, guys, and I will hopefully see you at school tomorrow. Looks like the snow has let up, so thank you very much.